Our next speaker is Tom Jones. Tom founded the Intermountain Native Plant Summit in 2001. He has worked in native plant material development at the ARS Forage and Range Lab in Logan since 1986. He is now working on native forbs with Doug Johnson and Sean Bushman, in addition to his work with native grasses. Please welcome Tom Jones.
Thank you, Francis. Today I'm going to be speaking about a study we have going out of the lab in Logan. You can see there are several co-authors on this study. Performance of 39 bluebunch snake river wheatgrass populations at 3 contrasting sites in the eastern Great Basin. In the seed industry, there's something known as workhorse plant materials. These are plant materials that are widely used and are bought and sold in fairly large volumes. And so this kind of relates to the RC's "Don't Fence Me In." I like that. I'd never heard that before. So anyway, Paul Kraybacher, who's here today, he put out some contract bids for these 5 workhorse plant materials. So these are really official workhorse plant materials for the BLM at the present time. And you can see them here: Anatome, Germplasm, Bluebunch, Discovery, Snake River, Bannock, Thick Spike, Recovery, Western, San Luis, Slender. The last 4 are cultivars. The first one is a pre-variety germplasm. That's why there aren't quote marks around it. It says Anatome germplasm. And I noted the restoration gene pools, which is, what Val was speaking about, that we developed first in the, about 10 or 12 years ago, I guess now. So I wanted you to understand, first of all, that there really are workhorse plant materials, and this is a widely used term. So the 2 workhorse species that I'm going to be talking about in this talk are the first 2 in blue: bluebunch wheatgrass and Snake River wheatgrass. Snake River wheatgrass, this has already been alluded to, but you may or may not know it's often used as a surrogate for bluebunch. So Val said it's not native where he is. It's native basically where Idaho, Oregon, and Washington come together, those 3 states, but it's been found to be adapted to a much wider area than that. It's similar to bluebunch in terms of its phenology, and it's a cool season bunch grass. So the 3 contrasting environments are shown here. The plots were established from transplants that were reared in a greenhouse, and they were put out in the spring of 2011 at these 3 sites: Malta, Idaho, which is in southeastern Idaho, which is about 11-inch precipitation site, and that's what I'll be referring to as LRE. That stands for Low Resource Environment. The middle environment was near Nephi, Utah, at about 14 inches precip, the medium MRE. And the high environment, the HRE, local to us in Logan, near a town called Millville, at about 17 inches. So as you can see, these sites were chosen to reflect a range in precip. And what we did is we've measured above-ground biomass twice now. At the end of the growing season, the year they were transplanted, which could be called the establishment year, so they weren't harvested until October. But in the next year, they were harvested in July after seed maturity. Okay, and the plants went dormant, after seed maturity. In the design of the experiment, we had 12 replications of the 39 populations and 12 plant plots, a 6x2 arrangement. And these plants were all spaced 40 centimeters apart. We used a randomized complete block design for statistical analysis, and this was done, like I mentioned, at the 3 locations. For us, this is a pretty large study, over 16,000 plants that were harvested at each harvest. So these 39 populations, 34 bluebunch wheatgrass and 5 Snake River wheatgrass. Okay, and then go through some of these populations. Some of the populations were local blue bunches for the 3 test environments. So we had one local for the LRE, one local for the MRE, and one local for the HRE that were from the vicinity of those tests. And this is what we call the primary restoration gene pool. As Val explained, this refers to local material. If you're interested in this concept, there are a couple of publications back on the literature table about the restoration gene pool concept. A second group of plant populations were some workhorse plant materials of blue bunch. Beside anatone that we saw Paul Kraybacher requested, some other workhorse plant materials of blue bunch are P7 germplasm, Goldar, Whitmar, and these would normally be considered the secondary restoration gene pool unless, of course, they're being used in the locality where they were originally collected. But these materials mostly originate from the state of Washington and surrounding portions of the neighboring states. The next, workhorse plant materials of Snake River wheatgrass, which I mentioned is a common surrogate for blue bunch. And the 2 cultivars here are Seacar and Discovery. Because they're substituting for another species in practical use, they qualify as the quaternary restoration gene pool. There are different taxon, but they have similar ecological function to blue bunch wheatgrass. Another group, we had 2 populations of Snake River wheatgrass developed through hybridization with its closest relative, which happens to be thick spike wheatgrass, and these are denoted by an X following them. When we do this kind of manipulation across normal genetic boundaries, this is what we call the tertiary restoration gene pool. Actually, that's relative to Snake River wheatgrass, not relative to blue bunch wheatgrass, but just to give you an example. 2 blue bunch wheatgrass populations from the Columbia Plateau of Washington, Wahluke and Boardman. These are commercially available. That's why I included these. And then 3 from the Snake River Plain of Idaho. One from the upper Snake River Plain, INEL, where Amy was doing her research. One from the middle Snake River Plain, and one over here at Marsing for the lower Snake River Plain. And then we also had what we call cycles, which you can think of as generations of recurrent selection. This is what Val referred to as breeding. And 3 blue bunch wheatgrass populations. So we did some selection. This is what you call artificial selection as opposed to natural selection. In anatone and P7, and another population from Washington from a very dry site called ACC, or accession 238. They were selected for fecundity, or ability to reproduce in a competitive matrix the year after they were established. And this would have been done for multiple cycles or generations. So I want to go through their performance of, first of all, the 3 local populations at 2 sites. So remember I said there was a local population for the LRE, the MRE, and the HRE, and you can see those from left to right at the bottom. You can see in 2011, which was the establishment year, that the productivity, which is on the y-axis, that's biomass in grams per plot, was much lower at the LRE than at the other 2 environments. The MRE and the HRE. We didn't get a very big differential between the Nephi and Millville sites that first year. In 2012, at the low resource site in Malta, Idaho, we had a problem. We lost our data for that site for this year. So all I can present for 2012 are the 2 higher precip types, the MRE sites, MRE and HRE. But you can see the 3 populations from the LRE, MRE, and HRE from left to right. If you look within a site, for example, comparing the blue bars, they increase from left to right. You can see that the material from the higher precip site produced the most at Nephi, and it also produced the most at Millville. And so you have I'm trying to show you that the plant materials responded to the site, meaning that Millville was higher in terms of productivity than Nephi. The red bars are taller than the blue bars because it's a wetter site. But also, this shows that how the populations from the three sites differ. You can see that progression from left to right. So the first thing we did was to calculate correlation coefficients among locations and years. And then we had 5 location year combinations because, again, we lost the data at the low precip site in 2012. So we just have the 2011 data for the low site. And so the correlation coefficient is measured on a scale from -1 to +1. A +1 being a positive correlation, -1 being a negative correlation. And if you're right in the middle at 0, that means there's no correlation at all. The two traits that you're correlating are really completely unrelated. So what I wanted to show you here, first of all, looking at some of these, I can get this to, it was working before. There we go. Okay. So if you look at some of these three right here, notice that the highest correlation in 2011 is between the medium and the high site. And so those two sites, and this is correlated across the 39 populations. And the lowest of the three correlations is between the low and the high site. So that tells you it's pretty much what you expect. The low and the high are the most different. But it also tells you that the medium site is more similar to the high than the medium site is to the low. In other words, 0.71 here is greater than 0.51. Okay. Now, if we go to 2012, we can do similar correlation between the medium and high. Again, we didn't have the low site in 2012. We see a very high correlation between these two sites at Highville, at Nephi and Millville. This 0.85 here in the lower right. Okay. I point out a couple other things. We're getting high correlations between the years 2012, and these are the correlations in brown, 0.88 and 0.75. So what I'm trying to say is all of these combinations of environments are positively correlated. We didn't see the situation where a plant population that did very well in one environment do extremely poorly in the other. They tended to be positively correlated, not negatively correlated. You see no negative numbers here. So after looking at these correlation coefficients, I decided to calculate a stability index. And so what I decided to do is take the performance at the medium site and divide it by the performance at the high site. Now, I would have done the low site compared to the high site, but remember, we didn't have any data from the low site in 2012. And multiply that by 100 to put it on a percentage basis, and that's what I call the stability index. So you see here a code of many colors, and you'll continue to see the colors through the rest of the talk. And I want to bring some of these to your attention. On the left-hand side, you have these Snake River populations which have some thick spike in them. I introduced this as tertiary restoration gene pool material, and they have an X at the end of their names. You can see at the bottom. The next three are Snake River wheatgrasses in yellow. And then you have a series in brown. These are the cycles of selection in P7. A series in purple. This is selection in ACC 238. You have 3 black populations that you can see through the see here, and these are the ones from the 3 parts of the Snake River Plain: the high, or the upper, the middle, and the lower. Whitmar is in gold color. Anatone is red. Goldar is a teal color, and then these Wahluke and Boardman are in 2 different shades of gray. But what I want to point out here is we're getting very high stability. The plants are doing very well. The first 2, the E49X, E58X, very well at the medium site relative to the high site. The best of the group. Snake Rivers were so much lower. With selection, you can see in the brown, with selection we saw a decline in the stability index. But with selection in the purple group, not the purple group, magenta, I guess is that pink group, we saw an increase. You can see the 3 purples on the extreme right. These are the local populations, and they were really all about the same. So that gives you some idea. But stability index doesn't tell the whole story, because you can have a high stability index because you have a high performance both at medium and high sites, or you could have a high stability index because you have low performance at medium and high sites. Percentage-wise, it comes out to be the same. So I thought we should also consider the mean biomass of the sites to kind of separate out these 2 possibilities. So I decided to regress mean biomass on the stability index, and that's where this line through the middle, that's the regression line, that's the best fit of the data. And what we found was a positive correlation, that R number in the upper right-hand corner. It's not a large correlation coefficient, but is statistically significant, denoted by the asterisk there. And you see the same colors there that we had before. I'm not going to be able to get this pointer to work consistently, but you can see the upper end on the upper right is bounded by the 2 tertiary restoration gene materials. Those are the green diamonds. And you've got the one next to it, which is the brown cycle selection out of P7. Then on the lower left-hand side, you've got the black materials, which are the Idaho Snake River Plain populations. You've got Goldar and Whitmore down in that lower left. And a couple of those others that are the generic blue, those are also selected out of these Snake River Plain populations. Now some comments were made a little bit earlier about how selection reduces diversity. And I may have misconstrued the comments, but selection itself in a plant population doesn't necessarily reduce the diversity within that population, the genetic diversity. It can, particularly if it's not done correctly. And what I mean correctly by is to recombine or allow plants to pollinate a great enough number of plants to maintain genetic diversity. So when you go to the next cycle or generation, you still have a lot of genetic diversity remaining in your population. So think of a human population. I use this example. My grandfather came from an island I was just talking about at lunch, of maybe 1,500 people, half of which were black and half of which were white. And if you go back there today to a neighboring island named Spanish Wells, this is in the Bahamas, and you see some of the lingering effects of inbreeding in the human population, because the population size wasn't big enough after generations and generations of not having new people come in. You see this effect of generations of inbreeding. but it's a matter of having large enough population size. So that's what we need to do this correctly. Now I put this example up here. It's from corn, and it's done over 100 years. This is a long-term experiment. It's a very famous experiment in the discipline of plant breeding, and going back to the 1800s, they started this experiment to see if they could select, they would want to select for two things. One is oil and one is protein. So those are the two colors there. And they did this year after year after year. You see there are a lot of jiggles up and down here. It wasn't a straight line when they evaluated it. But you saw that even after 100 years, there's still genetic variation. And that's because they did it right. If you use too small of genetic, or too small of numbers that you recombine, then you're going to get a genetic dead end. And that's where the inbreeding problem comes in. Okay? If you do things right, and of course you have to monitor what you're doing to make sure things are going as you think they're going, then you don't necessarily have these kinds of problems. And so I want to show this in these graphs. So one of the co-authors, Ivan Mott, and particularly Kim Thorstad, who's his technician, is responsible for a lot of these data. So these are cycles of selection in P7 from left to right, and this is what's called similarity index. This goes from 0 to 1. So complete similarity would be at the top. That means there's no genetic variation left. Everything's similar. So we want to make sure the line isn't going up. We want to keep it as low as what we started with. Okay? So I've got 3 of these from 3 series here. So you can just take a look at this. And this is for the ACC 238. Anatome, we don't have as many cycles, but you can see what I mean. What we're trying to do is keep that line from going up, and it seems to be working. Okay? Okay, so then I've got a bunch of a series of slides that let's see if I can. Okay. I'll go through these real quick. This is the low resource environment in 2011. The black line across the top is the mean. And you can see where the black populations are, the local populations. The one with the greatest performance is one of those tertiary restoration gene pool materials. Okay, now it's not on. Okay. Okay, here we go. Okay, in the medium site, you see the same sort of graphs here. The black line across the middle for the median. Nephi in 2012, and Millville at 2011, the high environment, and Millville at 2012. So I'm just going to summarize the points here. You can see the general idea from these graphs, these conclusions. Plant material productivity reflected the resource levels of the 3 environments, and the 3 local materials reflected their environment of origin relative to one another. A calculated stability index was positively related to mean productivity. The Snake River thick spike wheatgrass tertiary materials displayed highest stability and were superior to other Snake River materials for stability. Among bluebunch populations, stability of P7, Anatome, Wahluke, Boardman, and the 3 local populations was high, but stability of Goldar and Whitmar, the older cultivars, was low. Stability increased with cycles of artificial selection in ACC 238, but declined in P7. Artificial selection did not appear to increase genetic similarity, or, in other words, reduce genetic variation. The E58X performed the best at the LRE and MRE, but not at the HRE. Discovery Snake River performed better than CCAR at the MRE and HRE in the establishment year, but they were not different in the LRE. Discovery and CCAR did not differ in the second year in any environment. Goldar performed very well in the high environment and very poorly in the low environment. P7 and Anatone performed similarly, except P7 exceeded Anatone in the middle environment in the establishment year. The three populations from the Snake River Plain performed poorly at all locations in both years. And productivity of the three local populations was inconsistent, but was most often near the mean of all populations for its respective location. Okay. Thank you very much. RC has a question, Doug.
Yeah, I wanted to follow up on the diversity question. So there's diversity within and there's diversity among. So I guess I'm sort of making a comment that if you're taking a whole gene pool of species and making a selection, you may not be impacting diversity within if you're doing that. You could very well be reducing diversity among.
Right, so RC's comment is that there's a difference between diversity within a population and diversity between populations. We've also addressed this issue in our releases. P7 that I've been talking about was developed as a multiple origin polycross to try and encapsulate a lot of the variation from the region in a single population, with the idea that natural selection could operate that and sort out the genetic variation that was useful for a particular site. But the larger point is, yes, if you use just a few plant materials over in restoration, that isn't reflective of the greater amount of genetic variation that's there. And I think that was Val's point as well. Okay. Thank you very much.